Hello, everyone, and welcome to another wonderful day of physical chemistry. So today we're going to be taking what we learned about harmonic oscillators last time and, well, trying to figure out a couple eigenvalues and expectation values. So let's go ahead and start with our general forms. So unlike a lot of our previous systems, the harmonic oscillator has a little bit more of a unique wave function. So we first of all have a normalization constant. Unfortunately, this one has a bit of a non-intuitive form of a solution. We do have an exponential in terms of a variable besides x, but it is related to x by a rather messy constant. And of course, we have our Hermite polynomials, which essentially change depending on which energy state we're in. Again, higher energy states, more terms present in our polynomial, and the more nodes and varied the shape of the function becomes. We do, however, have one fairly simple eigenvalue of the system, and that is indeed our energy, which helped us identify the wave function itself, which is dependent upon the energy state and the vibrational frequency, which can be given as a ratio of the force constant and the reduced mass of our vibrating bond. So again, there's a lot kind of going on to this system, but we can actually determine the expectation value of almost any other function using the tricks that we learned previously through quantum mechanics. Most notably, if I want to figure out the average value of an operator, I can go ahead and apply that operator to the corresponding wave function. So let's go ahead and start with a rather simple operator to try and apply. Who doesn't love the good old position operator? So I can apply my position operator to this function. And not too surprisingly, position is not going to be an eigenfunction of this wave function. However, we can rearrange the system to try and find an average position value. So when we do this, we're going to want to try and identify terms that we can pull out and terms that we can combine. So not too surprisingly, I can combine my two normalization constants and pull them out front. That's a classic feature of most functions. However, our Hermite polynomials and the x terms are going to have to stay in, but the Hermite polynomials can be squared, and we can remove the 1/2 on our wave function itself to give a little bit more of a simplified form. However, now we run into this little pesky issue that my position is both in terms of x and in terms of y. Well, that's a little annoying. However, it turns out because the fact the Hermite polynomials in terms of y, in general, the easiest form is going to be turning our x values over into y values. And we can do that by noting that the position is related to alpha y. Simultaneously, that means that the first derivative of the position is related to alpha first derivative of y. And then we can then input that into our function. And since we're integrating from negative to positive infinity, well, our bounds don't change at all. So we then generate a slightly different function. However, it is worth noting by doing the substitution, we do generate a squared alpha term. So that is essentially worth acknowledging. One alpha comes from the x and the other one from the dx. However, doing that, we generate a fairly nice solution. Now, part of the issue here is I'm integrating from negative infinity to infinity. And as I commented before, one of the key parts about this function is it follows what's called a Gaussian formula with e to the negative y squared. So one of the things we'll typically do is split this up into 0 to infinity and negative infinity to 0. And when you do this, I do want to comment, there is a kind of cool feature of the average position, which is you'll notice that this function is the same as this function. However, since I'm going from 0 to negative infinity, let's go ahead and figure out what happens, or 0 to positive infinity. Well, this value is squared, so it doesn't matter whether I'm going to positive infinity or negative infinity. So that's going to be kind of invariant. However, I have an extra term here. Well, this means that when I have the positive infinity, this is going to cancel out with the negative infinity from the other expression. This is what's called an asymmetric function. So when this function is positive, this function is negative. So when I add the two functions together, the answer is 0. So this means that my average position is 0, which actually makes sense because 0 is essentially the default resting position of a harmonic oscillator. So this is kind of a long way of going back to saying that we get the answer we would expect logically. So sometimes logic is more powerful than mathematics. I'm vibrating about my 0 displacement position, so my average value should be 0. And this actually makes sense. It may not be what happens in a real system, but it does make sense for the harmonic oscillator. However, a more interesting value is actually going to be, instead of the position, it's our good old friend, the variance, or the mean squared displacement. So instead, we're going to take the average of the squared position. So this is going to give us a simple result where now we're going to integrate from negative to positive infinity. Instead of about x squared. So we're going to start with a similar trick. We're going to combine our functions, pull our normalization constant out front, combine our Hermite polynomials, and combine our exponential functions. But now I've got x squared and dx. I'm going to use my same substitution, except for now I have a cubic relationship with alpha. Again, an alpha squared from the x squared and another alpha from the dx going to dy. So this gives me another integral to try and solve. Now, the actual first step of this solution gets a little bit tricky because we're pretty good at solving the actual integral of the Hermite polynomial with the exponential term. What we're not so good with is introducing this extra y. However, using a set of polynomial expansions and contractions, it can be shown that this will turn into a v plus 1/2 expression, with, again, our cubic alpha being pulled out front. If you'd like to see how y squared becomes v plus 1/2, I recommend you kind of see your book. It's a rather long proof, and I want to kind of keep us moving on track, despite all my tendency toward tangents. However, driving this y squared to a numerical value gives us actually a big advantage, because it turns out we actually already know how to solve this system. It turns out we did this while normalizing our function. So this gives us a general solution of v plus 1/2 times the square root of pi times 2v times the v factorial. Now, the reason that this expression, as weird as it is, should look familiar is because it's kind of what we got when doing our normalization constant. So we're going to start to see a lot of terms kind of cancel out when I put in my normalization constant. One of the alpha terms is going to drop out. The 2v and the v factorial also drop out, as well as the pi halves. So we're left with an actually rather simpler expression for the variance. So this is just going to be alpha squared times the vibrational quantum number plus 1/2. All right, that doesn't look too bad. And then we have to account for the fact that we actually should probably remind ourselves of what our alpha value was. So our alpha value was related to the square, to the quartic root of h bar squared over mf. So I'm going to essentially, by squaring the function, reduce it to the square root of this value. And then what I can do is try and simplify things out a little bit more. I've got the square root of h bar squared. All right, that's not too bad. And then I've got my mass, which again, we're usually referencing as reduced mass times the force constant, showing up as a square root in the denominator. So this is actually kind of a nice, simpler description of my variance. Now, you might wonder, why do I care so much about the variance? Well, there's actually two reasons. The first of which is I do want to emphasize that our variance is dependent upon our vibrational level. So this means that as we kind of expect, as our vibrational system, as we go to higher and higher energy states, we're spending more and more time away from the uh, center of the oscillator. And that's really one of the things that the mean variance kind of tells us, is more about, on average, how far you're spending away from center. And we are indeed seeing this go up, and it gives us a numerical value to try and describe that. The other thing is it tells us a lot about the average potential energy, because it turns out that, again, our average potential energy is 1/2 kf(x squared). This was indeed the equation for the potential energy for a harmonic oscillator, so it still is going to hold. But since kf is a constant, it comes out of the average, and we're left with 1/2 our force constant times the variance, which is kind of a cool way to get out the average potential energy of a system. Now we can go ahead and plug in our new numerical value for the variance. And what ends up popping out is, well, something a little bit ugly. But let's go ahead and try and find some key features. The one I want to focus in on is terms we can collapse down as we find a kf up here and a kf down here. But this one's in a square root. So when they cancel out, I'm left with square root of kf over the reduced mass. Okay, I have an extra 1/2 v plus 1/2 h bar square root of, oh wait, that's the reduced mass. Congratulations, we have an expression that should look fairly familiar, because I got my vibrational frequency back. Because again, this is that square root of kf over reduced mass. And it is worth noting that this expression itself should look vaguely familiar, because this is half the average energy. And this actually leads us to a rather cool and fairly important realization, that on average, half of the energy of a harmonic oscillator is in kinetic motion and half of it's in potential energy. And one of the very important features that is worth noting is that this is going to be true no matter the energy state I'm in, no matter the vibrational quantum number. The kinetic energy is always going to be equal to the potential energy, and both of them are consequently half of the total. And this actually is very important because it leads to is very important because it lets us figure out about, on average, how fast the system is. If I know the average kinetic energy, I get a lot of cool information like the average momentum and the average speed, which again is a very kind of cool way of looking at the system. But it is also worth noting that this is a special case of a virial theorem, which is if you have any potential energy, V equals any constant times the position to an exponential power, you can actually relate the kinetic energy to the potential energy, as twice the kinetic energy is going to be equal to the polynomial factor times the potential. In this case, we are a quadratic equation, so B was 2, so potential is equal to kinetic. Again, a very kind of cool feature. However, one of the other things I kind of would like to talk a little bit about is tunneling, because it is worth noting that at any given energy level, our potential wall is not infinite, even if it is infinite over the large range. And this means that we are going to see some tunneling, even though our potential is greater than our energy. However, a very key point is what's called the classical turning point. So this is the point at which classically a spring would turn back. So this is, again, where our potential is equal to our total energy. So again, this is the point at which it would turn back. And we can figure out what that position is by knowing my total energy, which I have an eigenvalue for, set equal to 1/2 kf times the classical turning point squared. So we can then rearrange the equation, identify our classical turning point as plus or minus, because I'm going to have two classical turning points, the square root of twice our total energy over kf. And then we have the joy of plugging in our actual expression for our total energy based on our quantum number and the vibrational frequency. Now what we can do is turn this into an actual probability. So the probability of being found outside the classical turning point can be related as 2 times the integral from our classical turning point to infinity times, again, our probability density. Now, you may end up asking the reason why 2 times, because remember, this is going to happen once from x to infinity and one from negative x to infinity. But those should have the same probability densities, so we combine them to a simple 2 times. However, as you'll see later, it's going to be a little bit easier if instead of using x here, we use y. And again, it's for a lot of the same reasons as earlier, because we don't like integrating Hermite polynomials with respect to x. So we can go ahead and turn our dx into alpha dy, and then we just need to find our classical turning point, which I accidentally gave you too early. So again, just as a reminder, y is going to be equal, or x is equal to alpha y, or y equals x over alpha. So doing this, we can actually take our equation for our classical turning point over alpha, for our classical turning point in terms of y, by just taking the Cartesian turning point over alpha, which we can get by taking our general equation and dividing alpha, which I brought inside the square root as alpha squared, because alpha squared square root is alpha. Now, one of the reasons why is we can then turn this alpha into, in terms of vibrational frequency over kf, and then we can watch essentially all the chips fall as a lot of features start canceling out. So our Planck's constants cancel out, our omegas cancel out, and our kf's cancel out. So when we do this, all we're going to be left with is our classical turning point in terms of y is going to be the square root of twice our vibrational constant plus 1/2. Now, this is kind of a long way to kind of get back to trying to take this integral of our equation. But this gives us a lot of power in trying to figure out the probability of finding the system outside of a classical turning point. Now, the actual integral, as you would expect, is going to be dependent upon which vibrational state we choose. So let's go ahead and do the example for a simple form. So let's take for the ground state, v equals 0. So under v equals 0, well, this whole function is 0. 2 times 0 is 0. Square root of that is, well, v is 0. This is 1/2. 2 times 1/2 is 1. Square root of 1 is still 1. So for our ground state, our classical turning point is 1, which is going to be a very useful feature. It isn't so easy for the excited states, but it's not too bad of an equation to determine. So we're going to be looking at, I'm going to pull the alpha out front, 2 alpha times the integral from 1 to infinity of our probability density with respect to y. So then we can go ahead, and this isn't actually too bad for the this isn't too bad for the ground state, because our function is just going to be based on the exponential of the negative y squared over alpha pi halves dy. So our alpha is going to come out and cancel. Square root of pi comes out. That's fairly nice. And then I'm left with a numerical integral. So it turns out that this guy's a little bit harder to solve, but there's plenty of numerical solving techniques you can apply. And what you'll end up finding is that this gives us an integral, a probability of 0.16. So this is essentially another way of saying that 16% of the time, for the ground state particle, the wave function will actually be found outside of its classical region. So this is a lot of math to actually show something I think is fairly important, which is that we often think about uh, a, uh, a vibration occurring like a spring, moving in between its classical turning points where all the energy is given up. But because of the inherent quantum nature of our vibrating particles, they actually spend a significant amount of time. So about 8% of their time is spent further out than that classical turning point, and about 8% is spent further in than that classical turning point, which is honestly a bit of a shocker, but very important to keep in mind. So this kind of brings the end our simple description of the potential oscillator or harmonic oscillator as kind of a simple function of description. What we're going to do next time is take it from a simple mathematical expression to actually putting it to use and bringing up introducing the basic concepts of infrared spectroscopy. Until then, take care.